you familiar with 2D
He doesn't
materials?
know anything.
Okay, so in condensed matter physics, 2D materials are these ultra-thin materials that are only a couple of atoms thick or 1 atom thick. And the most famous example of a 2D material is graphene. Right. So if you imagine this is one sheet of graphene, this is another. When you bring them onto each other and twist them at some slight angle, the two lattices, and that's what's happening in this figure, they basically interfere with each other to give rise to a larger Moiré superlattice. So that's what's happening with this hexagonal structure that comes out of that. And what's interesting is that when you do this and you make Moiré superlattices with 2D materials, the angle in some cases will actually change the way the electrons behave in those constituent layers used to assemble it. So it fundamentally changes the electronic properties just by changing the geometry, which is weird because at the macroscopic scale that doesn't happen, right? So like copper in a paperweight and copper in the Statue of Liberty are the same, but here the geometry makes a very large difference. So it gives rise to these novel quantum phases, which in layman's terms is really just exotic phenomena like superconductivity, topological insulators, and a bunch of these crazy effects that we don't normally see. And what we do in our lab is instead of assembling these superlattices from graphene, we use TMD, which is transition metal dichalcogenide. This is another class of material. So we stack them into these devices to test the electronic properties, or basically put a voltage over TMD Moiré superlattices. So this is a sample design. I guess I'll go through each layer from top to bottom, but for reference, no layer is more than maybe 3 atoms thick, and then in the plane of the material, they're not longer or wider than maybe 80 micron. So it's about the scale of like a human hair if you look down to a microscope. So you start with this topmost HBN, that's hexagonal boron nitride, and it basically acts as a sealant over everything else as a protective layer. And you'll see in assembly, but it also helps assemble the device. Then you have a top gate. This is made out of graphite. Then the top BN, another protective layer, and also serves as an insulating layer. This Moiré core, which is what we're interested in, bottom BN, and then a bottom graphite, bottom BN. And then all of these are stacked onto each other and lowered onto a pre-patterned electrode, which is made of silicon or SiSO2 with platinum or palladium contacts. So if this is the cross-sectional view, this is the top-down view of the same device where you see it lowered onto the electrode.
Okay.
So these like
each of these layers is one layer of graphene.
Each of these layers, so it's not each is one layer of graphene.
Top gate and bottom gate is graphene.
Okay.
Oh, graphite.
To literally follow the same device, you start with this topmost BN, then you have the top gate, then the top HBN, then these 2 layers of TMD, which they're put onto each other and twisted, then the bottom HBN, which is the smallest blue rectangle, and then the bottom gate. So this is all lowered onto the electrode. And to use, not a perfect analogy, but it works here, the gates basically act as cables that you're attaching to this Moiré core, and if those are tiny cables, they attach to these platinum contacts, which are just larger cables that connect to other instrumentation that lets us put the voltage where we want it to go. And this is all designed using custom stacking software, so we basically upload the images of each layer, we make them transparent, and then we overlap them in the software, and then we go from there to do the alignment and actually build the device. But to gather the materials to do this is a challenge of its own. We use the Scotch tape exfoliation method. So say you start out with like hundreds and hundreds of layers for graphene or graphite, and you want monolayer graphene, you put it onto tape, you peel another piece of tape off, so a daughter tape from the mother tape, and you keep repeating that process until it's so thin, and this is what's happening here. Then when you place the tape onto silicon and peel it back off, it deposits 2D material onto the silicon. So that's what two-dimensional materials are, what a Moiré superlattice is and why we care about it. There's applications in pretty much every part of computing when you have superconductors and these other exciting effects, and then the design of our devices and how we get materials.